All right, so this is lesson one of module three, which is what is a mineral. So basically, we think about what a mineral is. A diamond is a mineral. So the properties that a diamond has, well, if we think about it, it's shiny, so it has a luster. It is definite chemical composition. It has a definite structure. It's solid. It's naturally occurring. Those are all things that constitute making a mineral. So it's a mineral. All right, so if we look at elements are anything that's on the periodic table. So that would be an element. And it really just can't be broken down into something simpler. So we've got all of these, on this periodic table, 118 elements altogether. So depending on what periodic table you look at, there might be more or less. And some of those are man-made. Some of that just depends on the age of the periodic table because they haven't been discovered yet. But there's a variety of numbers. 118 is about what we're at right now. These right here, 109 to 118, they are there. They just maybe haven't been naturally discovered in nature. And that's why they're kind of different down there at the bottom. All right, so if we look at the characteristics of a mineral, and we'll look at some minerals this week in lab, but a mineral has all of these properties basically on this bullet. So it's naturally occurring, it's inorganic, meaning that it has never been living before, so it's not like coal that used to be plant material or animal material. It has a specific composition, so it's made out of something specifically, always, like diamond, for example, is carbon. And then it has a definite structure, so chemical or definite crystalline structure, meaning that it's always the same shape. All right, so if we go into specifics of these, it's naturally occurring, just means that it's not man-made. It's found out in nature, and it was never from something that was living. So it has to be inorganic. So that's why coal is not a mineral, because it's made from plant and animal material. All right, and then the definite chemical or definite crystalline structure just means that it has a definite pattern. So it's cubic, it's hexagonal, it's got some definite structure, and it's always the same. So you're never going to find a quartz crystal looking differently. It's always going to be hexagonal shape. It might be embedded in a rock and not you won't be able to see that crystal structure. Sometimes you have to have a special microscope to be able to see that crystal structure. So it's not something that's going to be always obvious to your eye. But if we look at the atomic structure of it, it's always going to be the same. So it could be cubic, it could be hexagonal, it could be rectangular. There's a variety of shapes, but it's always going to be that shape. All right, and then they also have a specific composition. So it's always going to be made out of the same thing. For example, diamond is always made out of carbon. It's not made out of sometimes carbon, sometimes hydrogen. It's always made out of the same thing. Same with any mineral that you guys will look at or that we'll see. It's always made of the same substance. So that's really important. And so if we look at the rock forming minerals, there aren't that many. So there are about only, there's 3,000 minerals altogether, but only about 30 of them are actually common. So we see those a lot. And those other ones that aren't as common, a lot of times those tend to be our gemstones. So things that we might wear as jewelry. Diamond, for example, is precious. And so it's not something that's very common. So that's why it's fairly expensive. But if we look at this pie chart, what's kind of surprising, oxygen and silicon, we talked about this making up the majority of the crust of the earth. It also, since it makes up the majority of the crust, it also makes up the majority of minerals because it's pretty abundant. So we've got oxygen being 46% of the rock forming minerals. And that's in solid form. So when oxygen bonds with other things, it's, remember, minerals are solid. So the oxygen is bonded with something else to make it solid. And then we've got silicon, which is about 27%. And then you've got a variety of other things making up the other 28 minerals that are common. But you can see there's manganese, potassium, sulfur, calcium, iron, aluminum. Those make up others. And those are not as common, but we do see them often, especially like here where the rocks are really red. They have a really red look to them because they contain a lot of iron. and they're actually oxidized. All right, so these are our rock-forming minerals, and the most common minerals that we see are listed here. So quartz is made of silicon, oxygen, amphibole, mica, garnet, feldspar, olivine, pyroxene, calcite, and those are the chemical formulas that are given. So, so there's a variety of different types of mica, and there's a variety of different types of garnet. A lot of times those tend to be like gemstones are garnets. But you can see this is their chemical makeup. So like, for example, calcite is calcium carbonate. So it's calcium, carbon, oxygen. And there's 3 oxygens, 1 carbon, 1 calcium. And then quartz, this is very common. It's silicon and oxygen. So it's a silicate. But it's got 2 oxygens and 1 silicon, which makes up quartz. And we have quartz in a variety of colors, just depending on some other things that are kind of like blended in with it, and that's what makes it different, like rose quartz or smoky quartz or things like that. It's just kind of a blend of other minerals that might be around, but it still makes up quartz. All right, so magma is anything that's underground. So there's magma and lava. The only difference is that magma is underground. It's molten rock, but it's underground. So you can see in this picture, we've got some magma. And so when it crystallizes and cools, when it cools, it forms crystals. And those crystals might not be visible to our eyes, but through a microscope, we could see them. And there are what make up the minerals. So the minerals crystallize and form, the minerals that we see in different types of rock. Like, for example, granite. Granite has a whole bunch of different colors because it has a whole bunch of different minerals mixed in there. All right, so here is a piece of granite. And you can see on this, we've got feldspar. It's listing all the things that are there. So we've got feldspar. It talks about the texture. It's a phaneritic texture, which just means that it's large crystals. And that tells us that it forms underground, which we'll learn more about later. But anytime you can see any type of mineral in it, so you can see the different minerals, that means it formed underground. If you can't see minerals, like for example, obsidian, it's all one color, so it formed above ground. So that's how you can tell. If you pick up a rock, you can tell exactly when and how it formed. So there's other things in here. Hornblende is listed, mica, quartz. Those make up this piece of granite. And we know that it formed underground because we can see the different minerals. If we couldn't see the minerals, then we know that it formed above ground. All right, so so if we look at minerals that are in solution, this is kind of how we find veins through rocks often, is because we've got minerals that are dissolved, they're in solution, so the material, the water is saturated with these minerals, and this water is superheated. It could be, I guess it doesn't have to be, but usually it's superheated. It's near like a source of magma, and so the minerals reach the melting point, they dissolve into the water, and then the water seeps in through the cracks of the rocks. And when the water disappears, the minerals are left behind. So we get crystal veins that are found throughout rocks. And that's because of this supersaturated material. And when it's supersaturated, it just means that it's been heated and more material has dissolved than normal. And so therefore it leaves a lot of mineral behind when it finally cools or evaporates. And that's how we get veins of gold that we find in rock, is because it's a supersaturated, superheated liquid that contains gold, seeps through the cracks in rocks, and then when it leaves the gold behind, and then they're found in the little veins of the rocks. All right, so these are the things in lab that we will use to kind of identify our minerals. So crystal form, that's something that we really can't see unless we have a special type of microscope. So we probably won't see that. But we've got luster, hardness, cleavage, fracture. So that's basically how it breaks. Cleavage breaks in a nice flat plane, whereas fracture is just kind of like a chunk. Streak, color, and we'll talk about each of these in a minute. Specific gravity, texture, density, and there's special properties like, does it glow in the dark? Little things like that. Is it magnetic? Those are some special characters. So in the crystal form, we really, like I said, can't recognize the crystal form unless we're looking at a special like electron microscope or something that not even every university would have. So probably won't see the crystal form, but sometimes like for quartz, you can. It'll have a nice like crystal shape, but more than likely we're not going to be able to see that. Luster, that's how it shines or reflects light. So so if it has luster, it's going to show metallic. It's going to be kind of a shiny, looks like a shiny piece of metal, kind of. Whereas if it's non-metallic, it's going to look dull, not like a piece of metal. And so you guys will look at that in lab. And then hardness is how easily it scratches something. So how does it scratch glass? How does it scratch a penny? How does it scratch a piece of metal? And we use a thing called Mohs scale of hardness, and that just compares known minerals with unknown minerals. So, for example, talc, you can scratch talc with your fingernail, whereas you can't scratch quartz with your fingernail. So quartz is definitely much harder, and you guys will practice using that as well. So here's that scale, and you guys will use these common things. These are just some examples of some minerals that are common and what their hardness is. And so diamond is the hardest mineral. There's nothing harder than diamond as far as minerals go. And then talc is the softest. So here's some examples of things that you guys can compare to. So fingernail, 2.5 on the hardest scale. Copper, like a penny, like a solid copper penny. Or 3.5, iron nails 4.5, glass 5.5, steel file 6.5. So those are just some examples. Wool kind of fall within this range. We may have a couple things that are stronger, like quartz, for example, but you could just say it's stronger than 6. All right. So the other things that we're going to look at, cleavage and fracture. So up here you can see this is cleavage, and basically it breaks in flat planes. So you can see there's nice flat planes, and you can see here nice flat planes here. Whereas fracture looks like this. So this piece of obsidian down the bottom, it's not nice, flat, smooth planes. It's kind of conchoidal. So this is actually called conchoidal fracture, where it breaks like a curve. So that would be fracture, though. It's a type of fracture. So either it breaks in nice flat planes, which is cleavage, or fracture is just kind of wherever and not flat. All right, streak. So you can see these different types of minerals that are listed or shown here. And some of them have streak, some of them don't. So these have streak. These ones do not. And so if it leaves a streak, it also has a metallic luster. So if I were to ask you which one of these has luster, metallic luster, you would tell me these 3 here because they left a streak. The things that are not metallic, even though they might be shiny, they're not metallic. And so they are not going to show a streak. So you can see there's no streak on the streak plate. And this is just an unglazed piece of porcelain. And you guys will use this in the lab. And then this one also, maybe faintly, I see something. So maybe I would have to look up close on that one. But the other ones show no streak. So they would be, the luster would be metallic for these and non-metallic for that one. All right, and then color. Color is probably the most noticeable. It's probably also the most unreliable. So lots of minerals, like fluorite, for example, comes in, I don't know, like 8 colors. So it's not really reliable because there's so many different colors. Some things are pretty obvious, like sulfur. I have a piece of sulfur in my classroom. The back curio cabinet has a whole bunch of different rocks, so you can look through that anytime in between class. But color is, and sometimes it's obvious, bright yellow. The only thing that's bright yellow is pretty much sulfur. But other things come in a variety. So color is kind of the easiest to see, but the least reliable in telling you what the mineral is. All right, and then some special properties. So these are pretty cool. So if sometimes we have magnetism where the mineral like magnetite will be magnetic and a magnet will stick to it. Some other special properties. This is calcite. See how it portrays a double image? So you've got a single line here, and then when you put calcite on it, you get a double image, 2 lines. And so that would only be with calcite. So you would know you'd had calcite if you have that. And then we've got agates. Sometimes agates can be pretty cool. And then this is fluorescence. So notice how under a, like, not black light, but under a UV light, they will actually reflect. Kind of like if you have stars, or maybe when you were little and you used to have stars on your ceiling and they would absorb light. And then when you turn lights off, they would light up still. So that's kind of what these are doing. So they're absorbing UV light, and sometimes they reflect that UV light when you shine a light on them. Sometimes they will actually absorb that light and you can turn the lights off and they will actually glow for a little while. So that's pretty crazy. But some minerals do exhibit these weird types of properties, and they're pretty unique to that mineral. So you know exactly what mineral you're looking at when you see that. All right, and then texture is how it feels. So is it smooth? Is it rough? Those kinds of things. But like this says, it's pretty subjective. It might feel rough to you and smooth to your partner. So texture is a pretty hard one to kind of discern, kind of use as a test. All right, and then density and specific gravity. You guys practice measuring density when you did the measurement lab. So that's mass divided by volume. And so density is just reflecting how densely packed the molecules are. So galena, for example, is extremely heavy for its size. So it looks like this little rock, and then you feel it, and it feels ridiculously heavy for its size. So that has a high density. It's got lots of weight, grams, packed into a small volume. So it has a greater density. Whereas something like pumice that actually like floats on water, that's going to have a really low density. So it doesn't weigh very much for the amount of space it takes up. So the more tightly packed the molecules are, the more dense it is. And like I said before, that's mass divided by volume is the equation for that. All right, and then here it is. So M is mass, V is volume. So density right here is equal to mass divided by volume. And we use that to tell specific gravity. So specific gravity is just that ratio of mass to an equal amount of water, and that would be the specific gravity. And that's really common to use for minerals, because if you have a little tiny chunk of something, or if you have a big chunk of something, the density is going to be the same. So if it's the same mineral, so grams per volume is going to be small for this one. And then grams per volume, even though this is a bigger rock, it's grams per volume because it's larger. It also weighs more, but it's larger. And so when you do the math, those should be the same. And if it's the same mineral. And that's it. So hopefully you enjoyed that. And hopefully the lab, this helps make the lab make more sense. All right.